Go. Whatever you did on that, just remind yourself it could have been an actual quiz, and it wasn't. Some of you should be very happy about it. So last time, just to do this semi-quickly, because I have all this stuff on this little handout, we said we're going to put these numbers into a hat, and we looked at the probabilities that I would pick each of those numbers out of the hat. Okay, cool. So then, if I were to actually graph this, it goes from 1 to 4. So like the 1 would go up to 0.25, the 2 would go up to 0.25, the 3 would go up to 0.25, 4. So this would be a what kind of distribution? This is a uniform, so it's already symmetric. So if it starts off already kind of nice, it doesn't take a lot to make it look normal. Because the idea was, I don't know if you remember, we talked about like the ages in Florida thing again, and I said if you took a sample of 20, it's going to start to look a lot more normal. Once you hit 30, every distribution just about is going to start to look really normal. Because again, this is the part that students, it's really difficult to understand. The thing we talked about yesterday was, here's the ages of people in Florida. This is individuals, right? But then, so I asked one person, how old are you? And I put their age down. But if instead I asked 20 people at a time, how old are all you? And let's average that. And then I put that dot down. That's going to look more like this. And then if I ask 30, it's going to look more like that. So it's going to become, and why does that happen? Because the larger the sample gets, what should be true about its mean? It should actually be closer to the real mean, right? It's much harder for a large sample. So if I took a sample of 30 people outside, how likely is it that they have an average height of 6'10"? Not very likely. Are you guys with me? 30 people just roaming around and they're all 6 foot something or other. Like something weird's happening. But if I go out and take one person at random, so much more likely, it's much more probable that I'd find one person that was 6'10", but not 30 people that were all around 6'10". Are you guys with me a bit? Because if I take 30 men, then they should get closer. Their average height should be a lot closer to 5'9", the average height of American men. All right, let me stop there for a second. Please let that just make sense. We know that from day one. The larger the sample, the closer it is to the true mean. We know that. The thing we're going to get into now today is the nuts and bolts of how much does it actually change. So the standard deviation here, I'll call it sigma 1. Sigma 2 is how related to that. How is the standard deviation for this related to the standard deviation for that? This guy's standard deviation will be bigger or smaller? Smaller because more of the data points are together. What's the standard deviation measure? Yeah, how far every data point is away from the mean. So if all the data points get closer to the mean, obviously the standard deviation gets smaller. And then sigma 3 is going to be smaller than sigma 2. It's going to be even closer to the mean. And if I went crazy and I took every damn person in one giant sample, then the average is going to equal the freaking average. Then that's like standard deviation of 0. That's the extreme. If I take the entire population, how far off from the actual average will I be? 0. I'm taking everybody at once. You guys semi with me. So that's like the extreme. Okay. I like it. Now watch. Just to kind of get you in the flavor of what's on this handout, and then I'll give you this handout that I keep talking about. Help me out. If instead, so this is all about picking one piece of paper out of the hat. So what if I were to pick 2 pieces of paper? So I pick a piece of paper and I look at it and I drop it back in. I pick another piece of paper and I look at it and drop it back in. And I take an average of those 2 numbers. So what's the lowest average I could get if I take 2 pieces of paper out here? What's the lowest numbers I can get? I'm taking 2 pieces of paper. So I get a 1 and then a 1. Remember, I'm dropping the first one back in. Are you with me? So I can get a 1, drop it back in, shuffle around, I got the 1 again. Right? Snake eyes. So one sample that could happen is 1, 1. And what's that guy's sample mean? What's the mean of 1 and 1? 1. That's crazy, isn't it? The average of 1 and 1 is 1. Ground shaking. So what else could happen? 1, 2 could happen. What's the average of that? 1.5, 1, 3, 2, or I could get 2, 1, or I could get 3, 1, or I could get 4, 1, or 2, 2, and so forth. I could make this huge list of sample means. So again, this is for individuals. If I take groups of people at a time or groups of numbers at a time, in this case just 2, just to make it fit on the freaking paper, right? Because that sample size gets really big after a while. If I take samples of size 2 and plot them instead, this picture is going to become a lot more normal. So let me just show you. Let me give you this, for me, very, very colorful. We're looking on the side with all the colors. The back side will be next. So I've got this picture, just obviously better because it was generated by Excel. Ooh. And then I've got this. Do you guys see this? Started in the middle here with all the pink going on. So all the numbers, I'm really, really, really desperate, obviously always want this to make sense. But my original picture, the data was all the individual slips of paper. Now my data is going to be the averages of the 2 slips of paper that I took out. That's my data now. So how many data points do I have now? 16 data points. So you can see I reconstructed the X bar and P of X bar down here. There's a lot more possible outcomes. I couldn't get 1.5 before. That'd be weird. Did the 2 like slice off a bit and I'm like, that's 1.5. No. Right? But you guys see what's the most commonly occurring average in the pink there? What's the most commonly occurring? Oh, you didn't get one. Oh, you're all like, I can't see. Everybody got one? Uh-oh. That's okay, thank you. All right. Everybody got one? Okay. So the most likely thing is 2.5. And what was the average in the beginning? 2.5. Now that's not always going to be true, but it started off nice and uniform. So now look at the picture. You guys see how that picture was constructed? How many 2.5s were there? 4 of them. So now that's the tallest bar. And wouldn't you say that this looks roughly normal? I like it. So it only took a sample size of 2 because it started off so nice. It's a big block. I took a sample size 2, it's already looking normal. If I took a sample of size 3, 2 things. This would get much bigger, because then I could have 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, 1, 2, 1, 1, 2, 2. That's enough. Holy shit. So this would get stupid big, and this would get even better normally distributed. I'm going to let all that stuff sink in, or try to. I love some of you guys are like, you will not penetrate my brain with statistics. Shit. Please, I want you. So obviously, let me see if you guys agree with me. Would you say the data is closer to the mean in this first picture or the second picture? Second picture. In fact, that's the highest bar, is right on top of the freaking mean, right? So obviously this standard deviation should be smaller than this one, and I calculated it. Do you guys see at the bottom? So the mean, now obviously, please dear God, if I average 1, 2, 3, 4, or I average 2 of them at a time, the average is going to be the same. Does everybody understand that? If I have a group of numbers, they could be ages, they could be shoe sizes, they could be numbers in a hat. If I average them individually, or if I average them 2 at a time, the average is going to come out to be the same number. Do you guys get that? Yes? No? Do we need to do a specific example? I don't know. All right, here's one. The average, the average does come out to be 2.5 if you average those together. But again, let me. If I took every single person's age and then averaged it, it would come out to some number. If I take every group of 2 people that I can, every group of 2 people, and average those averages, it's still the same people, is it not? Nobody was counted more than anybody else. Do you guys understand what I just said? Just because I'm taking 2 at a time, nobody was counted more than anybody else. If they were, I didn't take my pairs right. So the average is going to be the same as it was before. There's no reason it would be older or younger. I didn't take the older people more, right? Because they couldn't move as much. I'm like, I gotcha. You're all running away from me. I don't want you to win. I don't know. I got a weird scenario going on. There's no reason that any of you would not have been picked as much as anybody else. So the average is not going to change. So let me explain some of the symbols. And then I'll show you what it means at the very bottom there. So this symbol we know, but let me be much more specific now. That's the mean of individuals. And that came out to be 2.5. We calculated that. That's 1, 2, 3, 4, right? And we calculated, so I'm looking up here at the top. We calculated this last time. We did x, x p of x, x squared p of x. We summed them up, did all that business. So we came up with 1.118. So this is the mean for individuals. And this is the standard deviation for individuals. Now, this is still a population standard deviation, but it's for individuals from that population. Now I'm going to talk about this, which is the mean of all the sample means. So now I'm not just taking 1 person at a time. I'm taking 5 or whatever, or 2 like on this. So I'm not plotting a single person. I'm plotting a group of 2 or something. So that's what this means. This means the average of all the averages. So if I got an average age for you guys, average age for you guys, blah, 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 blah. Each one of those would be an X bar. It's a sample of size 2. And if I average all those averages, I'm going to get the same thing I had before. Of course I am. But what's true about the standard deviation? The standard deviation is going to get smaller because all the samples should get closer to the real average. So the new standard deviation is what I call it. But this is the standard deviation for samples. What happens to it is it's the old standard deviation divided by the square root of n. That's the formula. Now if you're still paying attention, at least most of you guys have your eyes open, and some of those are looking forward. That's good. This is the only difference, and the problem is right there. It's insane how long it took me to explain this. You're like, yeah, I was here. It took you a freaking long time. But this is the only change. And what was the standard deviation before? 1.118, right? For individuals. Now if I divide it by the square root of the sample size, and how big was each sample I took? 2. You get 0.791. Which is the standard deviation, if I calculate the standard, I did it for you, which is the standard deviation of all this. If I calculated x p of x and x squared p of x and did all that. It's kind of freaky. And look, what happens when the sample gets bigger? I'm going to divide the old one by a bigger and bigger number, so it will get smaller and smaller like we predicted before. The more sample I pick, in fact, if I took everybody, sample size, population size, it's going to go to the extreme 0. Let me see if I can push it a little bit. Somebody know what happens when I let n get really, really big? This thing gets really, really small. So if n was infinity, this would be 0. But, you know, approaching infinity. You can't let it be infinity. But we're not going to get into all that. I like that. Okay. Maybe. So let's do a problem right now so you guys understand what you're responsible for. Basically, everything we've just done, this whole thing is concept, concept, concept. Why does that make sense? Well, it makes sense that it gets smaller, and it makes sense that the bigger n gets, the smaller that should get. The closer my sample should be to the real average. All right, you guys semi with me? Okay, all right. Let's do a concrete example immediately. so we all see what the hell I'm going to do. So say I have a normal distribution where the mean is 19 and the standard deviation is 1.2. Let's do two problems here. A, picking one person. What's the probability that I get x less than 18? And then I'm going to do, go. Pick, what you got, Jeff? I don't know, man. 7 people. Probability that x is less than 18. X bar, sorry. So you see the difference here. This is I'm picking one person. So if this is ages of people somewhere, I know probably that their age is less than 18. This one is, I picked 7 people. What's probably that their average age is less than 18? So this is old news. This is old news. This is the classic z-score problem. Right? I'm taking one person. So all I got to do, when I draw this, I'm not going to draw this picture like this. And how do I know I can use z-scores?
It's normal.
Good. It's normal. Kick ass. If I didn't say that, oh shit. So what goes in the middle? 19. What do I put else down there? 18. And where is it? Yes. Okay. So 18. And I want the probability is less than 18. I like it, I like it, I like it. So now you'll start to realize why I did so many problems like this with you guys, because it builds off of this structure. So now what do I need to do with 18? I like it, so make it into a z-score. So it'll be 18 minus the mean. It's always minus the mean. Don't flip those around or else you're on the wrong side. Divided by 1.2. And why can I use the standard deviation they gave me? Because that's the one that works for individuals. Over here, I'm going to need this. I can't use the standard deviation for this problem because I'm dealing with individuals here. I'm dealing with this group of 7 shit. So I can't use this standard deviation because it only works for individuals. I'm going to have to adjust it over there. Let's finish this one out. What do you guys get for that z-score? Where? Negative 0.83?
Yes.
And now look it up in your z-score charts. You get 0.2033? And do I have to do 1 minus? No, because that is my question, the area below, and that's what the z-score chart always tells me. So about 20%, really, really rounding that bad boy, about 20% chance I would get somebody less than 18 years old. I like it. All right. So over here, 2 things. I don't like teaching this way to begin with, but I've put you all through the derivation of the idea, why this changes the way it does. Now I'm going to tell you the triggers. What tells you when to do this? Well, okay, I have to have taken a sample, and I have to ask a question about the sample mean. That makes sense. Here I'm talking about one person. It's not a mean of people, it's one person. So I don't have to do anything, I just do a normal classic z-score problem. Here I took a sample, well that's clue number 1. And I'm asking about the sample mean. Well there you go, locked up. So the very first thing I have to do before I do shit is change the standard deviation into the one that works for me. How do I change that standard deviation? Yeah, 1.2 divided by the square root of 7, because its sample size is 7. That's going to adjust it to be what it would look like if I graphed all of the samples of size 7. It would have a standard deviation of that. So somebody help me out. What is that? 0.453? Okay.
5.4 actually.
Uh-oh. 4.535? So 4.54? Yes, routing is good. Let me stop there for a second. For several seconds. Yes, sir?
Do you know it's a sample if it's greater than 1?
Basically, yeah. I wouldn't say, if I pick one person, I wouldn't say I took a sample of people, because I couldn't use the word people for a person, right? So it's got to be, yeah. In fact, watch. If you let n be 1, sigma divided by square root of 1 is still the same. So even if you use this for sample of 1, it stays the same. That, do you guys see that? I'm glad you said that. Thankfully, this thing, if I have one person, this thing better not change my standard deviation at all, and it don't. Just use awesome grammar. Hello. Yes?
I got lost on why you put the square root of 7.
All right, so we can't, unfortunately, the bad thing, some of you guys could handle some of the math behind some of these things. But the formula for changing the individual standard deviation to the one that works for groups of size whatever is to divide by the square root of how big your sample is. There's a lot of math that goes behind that, and it's actually related more to the variance, to be honest. I don't know if you guys see this. Do you guys see this? What's the square root of sigma squared? Sigma. And what's the square root of n? Square root of n. So the math is actually more related to the variance. You see, that's the variance there.
Is that formula you read on our formula sheet?
It will be, eventually, when we make one.
Just making sure.
Yes, it will be. All right. Now, here's the crazy thing. I don't even know if you guys really understand what I'm trying to say here. That is the only difference between this and that problem. I still do everything the same, except when I go to make a z-score, I don't put 1.2 there, I put 0.454, the standard deviation that is true for that situation. That's crazy. The concept is crazy, but then the actual nuts and bolts, easy. Please, and some of you guys are still like, no it ain't. It's because you got all the other shit in your head, which is good and bad. So now I can set up my picture. The mean is still what? The mean is still 19. That doesn't change just because I took groups of 7 people at a time. And I still want 18, and I still want below 18, right? But now when I go to do a z-score, it'll be 18 minus 19 divided by 0.454.
Zero, 139.
No, something went wrong over there.
0.01.
No.
Oh wait, negative 2.2.
Negative 2.20?
Yeah.
Okay. I like it. Let me let you guys. Is everybody getting that same thing that's playing along with it? Yes.
So that you read it as in like the probability that you get a mean that is like
Yes, exactly. Because I'm taking a group of 7 people. So how many groups of 7 people could I have picked? Every possible group of 7 people in that population. Are you with? So if I take a group of 7 people from the United States, it could have been any group of 7 people. I need to compare my group of 7 people to every possible group of 7 people. Well, the picture's not going to be the same. It's going to be skinnier. Because every group of sample size, a sample of 7 people should have an average closer to the real average. So I can't use this standard deviation. I must use the one that's true for groups of 7. Please understand. I've told you the idea behind it, which is weird, but hopefully some of you guys went with me on it. Then I told you the nuts and bolts, what actually happens. And now you realize you just got to look for the triggers. Did I take a sample? Am I asking you about the sample mean? Then you change the standard deviation, and then all the steps are the same. You just use that new standard deviation. So when you look up negative 2.2, what do you get?
0.0139.
Oh, you're doing that.
Yeah.
0.139?
Yeah.
That's why I was like, what the hell did you do? All right, so you were way at the end. So about what? About 1.4%. So this is related to, is it more likely to go out and find one person that's 6 foot tall? Or is it more likely to find 30 people that have an average height of 6 feet? It's more likely to find one person, right? that's 6 foot tall. It'd be much harder to randomly find 30 people. And I don't mean look for somebody, you're tall, come on over. I mean just point at people and have them come over to you. And you're like, oh shit, you're all short. Okay, I'm sorry. That would take a long ass time, right? It might eventually work, but it would be very unlikely. So this is saying it's much more likely to find somebody one person less than 18 years old, because that's not that far away from the average. But to find a group of 7 people that are less, their average should be close to 19. So that's why it's much less likely to find a group of 7 people that would be less than 18 years old. Maybe. At least you're all looking this way. Let's do one more example, and then you know me. I've got somewhere. Oh yeah, on the back of this. Oh, yes. I actually managed to save some paper. Let's do one more example, and then I'm going to unleash you on the back of that paper. Students unleashed.
So you only do the second one when it asks you for the sample.
When I take a sample, and they're asking a question about the sample meaning. I like it.
Yeah.
So now watch this. Let me do one more example, but this will be a one-parter. We know mu equals 32.7. Sigma equals 3.9. If we take n equal to 37, find the probability that the mean is, what you got, Jeff? Greater than, do it, 35. You did it. You did it. Now, the reason I want to do a problem like this, the last problem I told you it was normal. I'm being very upfront about this. Did I tell you this is normal? No. A big thrust of a lot of statistics is it normal enough? Because I got the freaking chart with all the answers just waiting for me to find them. That sounds awesome. Don't you wish every class, there's a chart with all the answers on them, but you can only use it. Oh shit, when is that true? So, is my sample size big enough? Does anybody remember the magic numbers? The sample size has to be more than 30, thankfully. Because we only have 37. It's like, please, no. So since n is greater than 30. Now, I haven't even said the name of this thing. We've been actually working with this. But everything we've done so far is due to something called the central limit theorem. And the reason that that name makes sense is if the limit as n goes to infinity will be the center of the data. Remember that extreme I said if I took everybody, then the average would be, bam, right on the right average, right? If I took everybody at once, wouldn't it be the exact average, right? So the central limit theorem, as I get larger and larger samples, they tend to go towards the center of the data. So that's why the standard deviation gets smaller and smaller and smaller. So the central limit theorem says several things. It says it's normal enough. Check. Since my sample size is more than 30, it says it's normal enough. It says that the mean of those is the same as the mean was. So the mean doesn't change. But the standard deviation now has changed. Because, of course, that one is for individuals, but I have a group of freaking 37. I need the correct standard deviation to use for that. So I don't have to tell you it's normally distributed if the sample size is big enough. I don't have to say a word. Now, if I took a sample of 12, I better somewhere say it's normally distributed already. Like the problem we just did a minute ago. All right, so how do I do this problem? What goes right in the middle?
32.7.
32.7. I want greater than 35. What do I have to do very first thing before I do anything else? find the new standard deviation. Because I can't get a z-score until I know what standard deviation I'm using. I can't use that one. Where's that at, Jeff? There you go. I can't use that one because that was for individuals. So what's the standard deviation going to be now? 3.9 divided by 37. I like it. Sure. 0.641. Right. Remember, standard deviation is always at least 3 decimal places. So if you want 4, it's even better. I love it. I'll let you soak all that in. That is the new step, which doesn't seem right because it took me a long time. It took me a class and a half to talk about the idea. But it ends up just doing this one thing to my problem. It changes the standard deviation. So now, how do I get my z-score?
32.7.
Yeah, my data point here. What's my data point?
35.
Yeah.
Minus 32.7.
This should always be the mean second. Divided by
0.64.
0.641. I love it. It's like 4 on one. It's going to be 3.92. I don't know. Ah, it's close. Is that even on your chart?